Alright, so we have a sphere with radius capital R, and then it has a volumetric charge density function, rho of R equals rho naught times 1 minus lowercase r over 2 times capital R. And rho naught is a positive constant, right? So we need to obtain the expression for the electric field inside the sphere in terms of the constants. And then we need to obtain the expression of the electric field outside the sphere in terms of the constants. And that should be greater than, actually. And then in part C, we need to compare these two equations, looking at point R equals R, which is the surface of the sphere, right? Because it's capital R. And then lowercase r is just measuring our reference point. What radius are we looking at? Interpret this. Okay. And then last question, if the total load of the sphere is Q, find the constant rho naught in terms of Q and R. Okay. So let's start with part A. So, well, first of all, so here's the diagram. This is the sphere, the charged sphere. And then this dotted surface here is the Gaussian surface we want to pick, which has the radius little r. And then the field, the electric field along that surface is coming out perpendicular to the surface in all directions. Now, if you don't understand why we pick a certain Gaussian surface, you'll understand in a second. I'll explain that. Okay, so if you write out Gauss's law, it is the surface integral of the dot product with the electric field and the differential area element vectors, that's equal to the charge contained in the Gaussian surface, Q, divided by epsilon naught, the permittivity of free space. Okay, and that will be equal to, so we pull out this epsilon naught, and we're solving for the charge here, in terms of we're integrating the charge density over the volume. So, but our variable is R, and we want to integrate with respect to V, so we need to do a substitution. So we need to find the volume in terms of the radius, take the derivative, and then you can get dV in terms of dr. So 4 pi r squared dr. Okay, so you plug that in here. So instead of dV, you have 4 pi r squared dr. Okay, and then you pull out the constants here, and you distribute the r squared here into the function. Okay, now you integrate, and this is what you get. And so you bring it back and you set it equal to the left side of the equation again, bring this back in. And now we want to work with this side of the equation. So the reason we chose the Gaussian surface that we did is because we always want to choose, well, first of all, it's a good idea to choose where the field is perpendicular to the surface, and therefore the dot product becomes just the regular product of the magnitudes, and you don't need to do a dot product. And we also chose the surface so that it's constant over the whole surface because there's a uniform charge distribution, and therefore you can pull it outside the integral. And then the surface integral of the differential area elements, that just becomes the surface area of the Gaussian surface, which is the surface area of the sphere of radius r, which is 4 pi r squared. Okay, so we've worked with the left side. Now we set it back equal to this right side stuff. Okay, and then we simply divide by this 4 pi r squared in order to solve for E, the electric field on that Gaussian surface. And so we get this first function, rho naught over epsilon naught times r over 3 minus r squared over 8 capital R. Okay, moving on to part B, looking for the electric field outside the sphere. So similar process, except that the charge contained here would be the charge of the entire sphere. So as you go further out from there, you're not getting any more charge. You've already captured all of that charge, no matter how far you go out. It's the amount of charge contained is always going to be just the charge of the total charge of the sphere from then on out. So you have your charge equation here, where we were solving for the charge, and it becomes all this stuff besides the epsilon naught, right? So it's everything here except for the epsilon naught. You just plug in r to that, because that would give you the charge at radius r, which is the edge of the sphere. In other words, all of the charge. So if you plug in r, then this is what you get. Okay, again, manipulating the left side of the equation, same properties apply. So E times 4 pi r squared, divide by 4 pi r squared, and you get the expression for the electric field outside the sphere of 5 rho naught r cubed over 24 epsilon naught r squared. Okay, so part C is asking you to compare equations A and B, looking at them at point r equals r. So basically what they want you to see is that the two functions, this one and this one, those are going to be equal on the surface of the sphere. And we know that because we used the surface of the sphere to solve part of this function. So we know that, well, it's easier to explain with this graph. So the electric field's building up as you get more and more charge contained in the Gaussian surface as you go out, and then boom, you reach the edge of the sphere and you're no longer getting more charge, and so the electric field must die off, right? But these two functions, so this is the part B function and this is the part A function, even though they're only defined, so this is only defined here and this is only defined here, I've just plotted them both so that you can see that they cross and they're equal here. But you should already know that because we used this point r equals r to solve for our equation B. And so the equations have to be equal. Okay, and then part D, if the total load of the sphere is Q, so that's the total charge, then find the constant rho naught in terms of Q and R. So just with a little manipulation, you can use this equation. Q over epsilon naught equals this stuff, and just get rid of the epsilon naught because we know the rest of the stuff is just the charge equation, right? So we know that the charge is equal to this stuff from part B, and then we just solve for rho naught. So it is 6Q over 5 pi r cubed. All right, well, that's it. Hope that helps. Goodbye.